Collaborative filtering recommends items by grouping similar users. But algorithm 44, Matrix Factorization, approaches the problem from the inside. It identifies the hidden, invisible traits that drive individual user ratings. This specific algorithm became the industry standard because it solved the most high-stakes data science contest in history, a competition with a $1 million bounty. In December 2006, Netflix issued a public challenge, improved their Cinematch recommendation algorithm by 10% to claim the prize. At the time, their systems were struggling to keep up with the scale of their growing DVD-by-mail library. While academic labs spent months on the problem, a hobbyist programmer named Simon Funk published a blog post revealing a mathematical shortcut. This single post essentially gave away the secret that put him in a tie for third place against the top researchers in the world. Funk's approach succeeded because he recognized a fundamental scaling issue. With a grid containing 8.5 billion potential entries and only 100 million actual ratings, the problem was too sparse for standard computational methods to brute force. This is the sparse matrix problem. In a grid where rows are users and columns are movies, 99% of the cells are blank. Most users have only seen a tiny fraction of the total library. Textbook Singular Value Decomposition, or SVD, is designed to simplify data grids. It factors a fully known dense matrix, labeled here as M, into 3 smaller, manageable components. But the issue is that SVD requires a complete dataset to function. If 99% of the initial matrix is missing, the math is undefined. For companies with massive, incomplete datasets like Netflix or Amazon, the textbook formula cannot be applied. Simon Funk realized he could retain the structure of SVD while ignoring the empty cells. By training only on the ratings that actually existed, he could compress those 8.5 billion potential entries into just 20 million parameters. This created an SVD-like model, a system that bypasses the holes in the grid and learns strictly from the visible data. In this model, every rating is treated as a dot product, the intersection of a user's taste profile and a movie's trait profile. These traits are called latent factors. They act like invisible dials for dimensions like action level or indie feel. The algorithm discovers these dimensions automatically through the data, rather than requiring humans to manually label every genre. In this comparison, Funk's method scales. Classical SVD holds all n by m cells in memory. Funk's version only requires 2 skinny matrices. Accuracy depends on k, the number of latent factors. Too low misses structure, while too high memorizes random noise. This assumes that human preference is not a mystery, but a series of interacting variables that can be mathematically mapped. This diagram approximates the sparse matrix R by multiplying a tall user matrix P and a wide item matrix Q. To fill a blank cell, it calculates the dot product of one user row and one item column, predicting a new rating. Looking at the mechanic, the red row of user preferences is multiplied by the blue column of movie traits. The point where they intersect becomes the score. This calculation is grounded in geometric mapping. It proves that the logic remains sound, even when we adapt it to skip over missing data points. Every unknown entry in the Netflix grid becomes a calculated approximation, an estimate of how a user would likely feel based on the hidden patterns found across the rest of the dataset. We have shown that 2 skinny matrices can theoretically reconstruct a massive grid containing billions of empty cells. Curious, but there is a missing step in the execution. If the original grid is 99% empty, how does the computer determine which numbers to put into those skinny matrices to begin with? The answer is an iterative learning process, gradient descent. As this diagram shows, the system predicts a known cell, measures the error, and nudges the vectors to improve. Funk's original training step did this in literally 2 lines of code. Matrix factorization provides the architecture for understanding preference, but gradient descent provides the engine to build it, a transition that moves us from simple recommendations into the world of neural networks. We know the theory of matrix factorization, compressing a massive ratings grid into 2 skinny matrices. Now we are going to build that engine in Python. You can follow along with the exact code in the GitHub repository. specifically in the Chapter 12 Movies Recommendation notebook. Before the algorithm runs, our starting data looks like this: the pivot table R. It is a massive, almost empty grid of users and items. Those scattered orange cells represent the tiny fraction of movies users actually rated. Our code has one specific job. It has to extract enough mathematical logic from those few isolated data points to confidently predict a rating for every single black cell on this board. To start, our algorithm knows absolutely nothing. We initialize our user matrix P and our movie matrix Q with small amounts of pure random noise. Now, test your intuition. We know a predicted rating is just the dot product of a user row and a movie row. Pause here and think. How would you write the line of code to calculate the error for a specific cell? We find the error by taking the true observed rating from our grid and subtracting our predicted dot product. Once we have that error, we use stochastic gradient descent to nudge our random vectors closer to the truth. We calculate that nudge by taking our learning rate, multiplying it by the error and the item vector, and subtracting a regularization penalty that keeps the values from growing too large and overfitting the data. Then we do the exact same thing in reverse. The item vector gets a perfectly mirrored update. The movie is nudged by the user's data, just as the user was nudged by the movie. These two symmetrical lines of arithmetic are the entire engine of Simon Funk's 2006 Netflix Prize breakthrough for decoding human taste. This diagram shows how those 5 lines operate at scale. We predict a cell, measure the error, and run the SVD update, looping this cycle over and over. But the efficiency comes from where this loop runs. It strictly iterates over the known ratings. It completely ignores the millions of empty cells during training. As seen here, training time scales linearly with observed ratings, compressing massive space into 2 efficient matrices. Once training finishes, every blank cell can be filled with an instantaneous dot product to immediately rank unseen movies. This lean handful of arithmetic can chew through 100 million ratings in seconds. But an engine this fast has sharp edges. It works exceptionally well on dense clusters of data, but it has a massive blind spot that will sink it if you aren't prepared. We will look at those exact trade-offs next. Every time you cue a song on Spotify, pick a movie on Netflix, or click a product on Amazon, an engine is running beneath the surface. These densely packed rows and columns, called embeddings, act as a universal mathematical translation of human taste. Other machine learning models in the pipeline can pull these exact vectors to train entirely different features by compressing sparse behavior into a dense, rapid-fire mathematical lookup system. When you move this architecture from theory into production, the mathematical limitations become obvious blind spots. The most glaring failure is known as the cold start problem. If a brand new user signs up today, they have no history. Without past ratings, the system has no data to calculate their latent vector. The exact same failure occurs on the inventory side. When a brand new movie is uploaded to the catalog, it has 0 historical views. The math requires past interactions to generate a prediction, so you have a recommendation engine built entirely to predict user taste, yet its mathematical radar simply passes over any piece of novel content, leaving new items entirely invisible to the algorithm. The second major operational flaw lies in the compression itself. The latent factors generated by the matrices are mathematically sound, but they are completely uninterpretable to human engineers. The model groups items together based on the numbers, but it cannot explain the logic. You cannot look at a specific vector and manually label it comedy or action. The features remain hidden. This effectively makes the model a black box. It successfully matches items to users based on the numbers, but it offers no human-readable explanation for why a specific connection was made. Maintaining this engine also requires heavy overhead. The base algorithm maps static, linear interactions based entirely on a snapshot of past data. To capture what people watched yesterday, the engineering team has to run constant, expensive full system retrains to absorb those new ratings into today's predictions. Set it too large, and it overfits, memorizing noise instead of new data. This leaves practitioners with a clear deployment rule. You deploy matrix factorization when you have massive, incredibly sparse grids of purely numerical data, paired with a high volume of repeat users. Conversely, if your platform relies on processing rich text or image data, or if your inventory changes constantly from day to day, you walk away and choose a different tool. Matrix factorization is an instrument designed explicitly for historical pattern matching. It works precisely for what it was built for, and fails the moment you treat it as a universal solution. By compressing sparse behavior into dense, highly scalable matrices, this technique became a foundational standard for model-based collaborative filtering. These structural mechanics and deployment rules are detailed further in the book 50 Algorithms Every Programmer Should Know by Imran Ahmed. But the cold start vulnerability remains an absolute limitation. The math requires historical ratings to function, which leaves us with a critical engineering problem. How do you build a system that can evaluate the actual content of an item before a single user has ever interacted with it? To answer that, we have to look at content-based recommendation, the necessary algorithmic counterpart designed to see exactly what matrix factorization misses.